Now we're going to look at implicit differentiation, but first I'm going to introduce a bit of notation. In these notes I'm sometimes going to write ddx with brackets after it, and by this I just mean differentiate whatever is in the brackets with respect to x. I sometimes might also write the brackets on top like this, d something dx. So, if that was y in the brackets, it would be dy dx, right? So, in general, it'll be some function of x in those brackets, and so if I write d dx applied to f of x, that will be equal to the derivative f prime of x. So a few examples: if I say d dx of y, that's just dy dx. If I say d dx of x squared, that's just 2x, or d dx of sine x would be cosine x. So when I say d dx of something, I just mean differentiate that with respect to x, whatever it is. The first example we look at is the equation x squared plus y squared is equal to 25. Now we can solve this equation for y in order to explicitly write y in terms of x. So in this case it's going to be plus or minus the square root of 5 squared minus x squared. You'll see why I write 5 squared in a second. So that's what we call an explicit expression for y in terms of x. It's explicit because we have y equals something, and that something on the right side only has x's, it doesn't have any y's on the right hand side. I write plus minus there because it could be the positive or the negative root. So this is actually an expression for two different functions. Those two functions are the positive and negative halves of a circle with radius 5 and centered at the origin 0, 0. If we look at the positive side, that's plus the square root of 5 squared minus x squared. We can differentiate that in the usual way using the chain rule. It's worth noting at this point that since y is equal to the square root of 5 squared minus x squared, this expression for dy dx is just minus x over y. Next, we try the implicit approach to the same problem, where we leave the equation as it is, and then we differentiate both sides with respect to x, and then solve that resulting equation for the derivative dy dx. So I say d dx of the left side is equal to d dx of the right side. Then I take that term by term on the left, so the derivative of a sum is just the sum of the derivatives, so that's d dx of x squared plus d dx of y squared, and the derivative of 25 with respect to x is just 0. So derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x is 2y times dy dx. So let's look at that term. How did we get that? Well, we know that y is a function of x. Even if we haven't written down explicitly what that function is, y in terms of x, we still know that y is a function of x. And so this expression, y squared, is something that can be differentiated using the chain rule. To calculate the derivative of y squared with respect to x using the chain rule, it's like our u function on the outside is squared, is v squared, and the inner function then v is just y. So by the chain rule, we get du dv is 2 times v, or 2 times y here, times dv dx, which is just the derivative of y with respect to x. So putting that together, we get 2y times dy dx. So let's go back to that expression we just worked out, which is 2x plus 2y times dy dx equals 0, and solve that to get dy dx in terms of x and y. So if I bring that 2x over to the right hand side, I get that, and then I divide both sides by 2y to give my answer that dy dx is equal to minus 2x over 2y, or dy dx is equal to minus x over y, which is the same answer that I got using the explicit version the first time around. The nice thing about implicit differentiation is that we can use it even if we can't actually write down an equation for y explicitly in terms of x. So the example that we'll do now is one where you would have a hard time writing down y as a function of x. The example is x times y plus y to the power of 5 plus 2x squared equals 7, and we want to find dy dx. So the first thing we do, as before, we differentiate both sides of that equation with respect to x. That d dx on the left can be applied to each term individually. So let's look at that first term, the derivative of x times y with respect to x. So this is the product rule that we use. So we say it's x times the derivative of y, which is dy dx, plus the derivative of x, which is 1, times y, which gives us x times dy dx plus y. The next term is the derivative of y to the power of 5 with respect to x. So this is going to be chain rule. Our inner function is just y and the outer function is y to the power of 5. So we differentiate with respect to y and we get 5 times y to the power of 4. Then we multiply by the derivative of y, which is just dy dx. The last term is easy. The derivative with respect to x of 2x squared is just 4 times x. So now let's put all those terms together. Next, we gather all the terms with dy dx in them on the left hand side in order to solve for dy dx. And we put the other terms over to the right hand side. Now we're going to factorize the left hand side of the equation. So we're going to take out that dy dx term from both of those terms. So we get dy dx times x plus 5y to the power of 4. So if you multiplied that out, you'd get back to the previous line. And finally, we divide both sides by that factor, x plus y to the power of 4, to get dy dx equals minus 4x minus y divided by x plus 5y to the power of 4. And that's our answer. So step by step, to do implicit differentiation, you first differentiate both sides of your expression, of your equation, with respect to x. Next, you want to solve that equation that you get in order to get dy dx equal to something. To do that solving, you first put all your dy dx terms on the left side and everything else on the right side. Then you factorize your equation on the left to get that dy dx term out, and then you divide both sides of the equation by that factor to get dy dx equal to something. And that's implicit differentiation.